Hello everyone. In this video, we will be looking at the final diagnostic test before we begin the video series on single and multivariable calculus. Today we'll be looking at some trigonometry, so conversions between degrees and radians, arc length, the unit circle, trigonometric identities. All of these are very, very useful and important when studying calculus. So to start, let's look at conversions. And firstly, let's go from degrees to radians. So for us, we will look at two examples. Firstly, let's look at converting 300 degrees into radians. Well, to convert degrees into radians, you simply take your value in degrees and you multiply by 2 pi radians divided by 360 degrees. The reason that you multiply by this factor here is because for every 2 pi radians, there are exactly 360 degrees. So these two values are in fact the same, so this quotient is 1. So it's okay to multiply any number by 1, it doesn't change it. So for us, we're simply converting from the unit in the denominator to the unit in the numerator. And the unit in the numerator for us is radians. So here we find that this becomes equal to 600 pi radians over 360. We can then divide both the numerator in the denominator by 10. And then further, we see we can divide the numerator in the denominator by 6. So this becomes a 1, and 36 divided by 6 is 6. So now we have 10 pi over 6. Finally, this can be reduced to 5 pi over 3 radians. So 300 degrees is equal to 5 pi over 3 radians. Secondly, consider negative 18 degrees. Well, one way to work this out is exactly as we did before. So we take negative 18 degrees, we multiply by 2 pi radians over 360 degrees, and then we just reduce. So this becomes negative 36 pi over 360, which can simply be reduced to negative pi over 10. So negative 18 degrees is negative pi over 10 radians. Now, we can also convert from radians to degrees. And we'll look at two examples again. So we take, for example, a value 5 pi by 6 radians. We wish to convert that to degrees. Well, we take 5 pi over 6 and we multiply by the inverse of what we multiplied by before. So we multiply by 360 degrees divided by 2 pi radians. Then we simplify. Well, the 6 in the denominator here can be canceled with this 36 here, which is really equal to 6 times 6. So 360 divided by 6 is equal to 60. So this is 60 now. And then further, we can divide this 2 by this 60, and we get 30. And then what we're left with is 30 times 5 pi, or 150 pi, divided by pi. This pi in the denominator comes from here, but the pi's cancel. So what we're left with is 150 degrees. As another example, consider 2 radians. So this radian value does not have a pi in it, which is perfectly fine. Radian values do not have to have pi's in them. So we proceed just as before. We say we take 2 times 360 degrees divided by 2 pi radians. Well, these 2's cancel, so what we get is 360 divided by pi degrees. And that's approximately equal to 114.6 degrees. Next, we will look at arc length. So arc length is simply given a circle of some radius r, and given this orange, the space between this orange and blue band, there's some angle here, theta. And what we wish to find is what is the length of the white part of the circle between the blue and the orange. We just wish to find the length. And the length is easy to find. You may recall that it's equal to just the radius times the angle. So, as an example, if you have a radius of 12 centimeters, and theta is equal to 30 degrees, this theta is often called the angle that the arc subtends. Then what we find is that L is equal to 12 centimeters times 30 degrees. But it's important to note that this L value is computed assuming that theta is in radians. So we have to convert 30 degrees to radians. But we know how to do that. All we have to do is multiply by 2 pi divided by 360. Doing so, we find that this arc length is 12 times 30 times 2 pi divided by 360. Well, you can divide our 10 by the numerator and the denominator, and also a 3, and 36 divided by 3 is 12. And the 12's cancel, this 12 and this 12, so all we get is 2 pi centimeters for the arc length. Next, we will look at triangle side lengths. You may have learned this as SOHCAHTOA. So here, given some triangle, some right triangle with some theta here and side lengths A and B, and the hypotenuse given by 24, we wish to find A and B in terms of theta. Well, SOHCAHTOA says that the sine of theta is equal to the orthogonal. So this the opposite side, so B here, the side opposite of the angle, which would be B, divided by the hypotenuse, which is 24. So that implies that B is equal to 24 times the sine of theta. Moreover, we know that the cosine of theta is equal to the adjacent side length, A, divided by the hypotenuse, which is 24, which means that A is equal to 24 times the cosine of theta. Then we can also look at trig identities. There are far too many to list right now, but there are a few key ones which are important to know, and I will just name them here. So, for example, let's say we wish to prove that the tangent of theta times the sine of theta is equal plus the cosine of theta is equal to the secant of theta. Well, the way that you go about proving this is by noting that tan theta is equal to sine theta divided by cosine theta. Then the identity above becomes sine squared theta, because we have one sine theta from the tangent and another sine just from this right here. So we have sine squared theta divided by cosine theta plus cosine theta is equal to secant theta. Then we can multiply this second term here by cosine theta divided by cosine theta. When we do that, what we get is sine squared theta divided by cosine theta plus cosine squared theta divided by cosine theta. So all I've done is I've multiplied the second term by cosine theta divided by cosine theta. Since that's 1, it's perfectly allowed. And this should still be equal to secant theta. Then these two terms have the same denominator, so we can combine them. And what we find is sine squared theta plus cosine squared theta divided by cosine theta is equal to secant theta. What we want to show is that this is true. Well, another well-known identity is that this numerator is actually always equal to 1. So it's always true that 1 is equal to sine squared theta plus cosine squared theta for any value of theta. Then what we're left with is 1 over cosine theta is equal to secant theta. And that's true just by definition of what secant is. Secant theta is just the reciprocal of cosine theta. So we've proven this identity here. Then we can also prove the following. So suppose we wish to prove that 2 times the tangent of x divided by 1 plus tangent squared of x is equal to sine of 2x. Well, one well-known identity is that this denominator can be rewritten as secant squared of x. That's just some identity. Another identity that we can use is called the double angle formula. So we can write sine of 2x, that's always equal to 2 times sine x cosine x. And this is called the double angle formula. Then, using both of these identities, what we're given becomes 2 times tangent x divided by secant squared x. And we claim that this is equal to 2 times sine x cosine x. Okay, well, what we found in the first example above was that secant x is equal to 1 over cosine x. So, using that identity in combination with the identity that tangent x is equal to sine x over cosine x, the left-hand side becomes 2 times sine x over cosine x divided by secant squared x. But because secant squared x is 1 over cosine squared x, we can bring the cosine squared up top, and that becomes cosine squared x. We can cancel one of the cosines with the one in the denominator here from the tangent. And this becomes, well, we want it to be equal to 2 sine x cosine x. And what we find on the left-hand side is that it's 2 sine x cosine x, which is exactly what we wanted to show. Finally, we will look at some actual values of the unit circle. This is something that you should certainly memorize, and you will use enough times to memorize some of them, regardless of if you want to, if you continue with learning calculus. And I will name just a few here. A good test of your knowledge will be that you have understood what I'm about to write down, and that you're able to say what the answer to these things are. So, one example might be, what is tangent of pi over 3? Well, we can break it down. We know tangent of pi over 3 is equal to sine of pi over 3 divided by cosine pi over 3. And further, we know that sine of pi over 3 is equal to square root of 3 divided by 2. And we know that cosine of pi over 3 is equal to 1/2. Well, the 1/2s here cancel out in the numerator and the denominator, so that we're left with tangent of pi over 3 is equal to the square root of 3. Next, we might be interested in what is the value of sine of 7 pi divided by 6. Well, we know that if you consider the unit circle, here is theta is equal to 0. If you go 180 degrees, that's pi radians. And 7 pi over 6 is pi over 6 past pi. So it's about here. And if you remember your unit circle, this should be a negative value. And since it's sine, we find that sine of 7 pi over 6 is equal to negative 1/2. Finally, we may be interested in what is the secant of 5 pi over 3. Well, this is rewritten, 5 pi over 3, this is rewritten as 1 over the cosine of 5 pi over 3. And the cosine of 5 pi over 3 is equal to 1/2. So this is 1 over 2, which is equal to 2. So the secant of 5 pi over 3 is 1/2. And this concludes the diagnostic test for trigonometry and also the diagnostic tests for this calculus series. If you found that you weren't able to follow along throughout any of these, then hopefully you have some blueprint for what you need to learn before you can continue. But if you did follow along or you only needed to remind yourself slightly of some of the information, then you should feel confident moving forward into the rest of the series. Thank you for watching.